Jai Hind, welcome to the course Network Analysis and Synthesis, and I am going to discuss compensation theorem of this course. So, what are the learning objectives of this theorem? First, we are going to state and prove as usual what is the statement of a theorem and how we will prove it. That will do, state and prove the compensation theorem. Then next we will discuss what are the steps carried out to verify the compensation theorem. Then we will do some examples. In this we will verify the compensation theorem, as well as with the help of compensation theorem we will try to find the responses of the network or circuit. Then in the last, what are the applications and limitations of this compensation theorem, that we will discuss. So, what is the statement of compensation theorem? So, if the impedance of any branch of a network is changed, look at here, from Z to Z plus delta Z, where the current flowing originally is I. So, this is the current I flowing in the branch where the changes have taken place. The change di at any other place in the network may be calculated by assuming that an EMF minus I into delta Z. We will explain later on why I have taken minus I here. That has been injected into the modified branch. Modified branch means where the changes have taken place, while other sources mean other energy sources, other independent energy sources are replaced by their internal impedances. So, this is the statement of compensation theorem, and we will discuss later on what are the applications of this theorem and what are the limitations. So, first just we go for the proof of this theorem. So, we have taken a circuit, simple, we have the VTS, Thevenin voltage, Thevenin impedance, and then we have the impedance. So, suppose the impedance of this network is changed from Z to delta Z. So, what we will do, first we find the value of current of this network, which is coming I is equal to VTS, simple series circuit. ZTH and Z, they are connected in series. So, simple calculation I. Now, we draw the modified circuit where the changes have taken place. So, impedance of this branch is changed from Z to Z plus delta Z. So, we find the current I dash. So, I dash be the simple this. So, this is the I minus I dash is the change in current. So, delta is I dash minus I. So, put the value of I dash here and I, and on simplification we get value of this is the delta I. This is the value of delta I. So, this is the VTH upon Z plus ZTS, which is nothing but this is the expression of I, and we have the remaining expression delta Z upon Z plus ZTH plus delta Z. So, this minus I into delta Z, that is written by a symbol Vc. So, Vc is minus I into delta Z. So, this is called compensating voltage Vc, or this is the EMF we are going to inject in the modified branch to find the changes in other branch of the network. So, this is your delta I. Now, we have now this is another circuit, or we can say that this is the circuit for the compensation theorem. So here we have injected this much voltage is injected into the modified branch where the changes have taken place, change has taken place in this branch. So we have injected this voltage in this branch. Then replacing, we have the VTS. So replacing the independent sources by their internal impedances. So it is in the ideal voltage source has zero resistance. So it will be replaced by a zero resistance wire. So it looks like a short circuit. Okay. It is basically the resistance of this wire is the 0. Now find the value of delta I. So delta I is Vc upon Z plus Zts and delta I. So this is the change in current delta I using the compensation circuit. We have another conventional approach. We have drawn the two circuits. One is the original circuit, then we find the original current, then we have drawn the change circuit where the after considering the modification, and we have find the change in current, then we have take the differential, and that is this much, and this is the circuit for the compensation theorem. So suppose you are required to verify compensation theorem. So there are three steps. First find the current of the original circuit, then draw the modified circuit, find the new current, take the difference, that is the delta I. And the third step is draw the compensation theorem circuit, and from this circuit find the change in current. If both the currents are same, then the theorem verified. Note, delta I, the change in current has the same as I. So direction of delta I will be the same as I. The direction of Vc is opposing to that of I. That's why we have taken this negative terminal. So this negative terminal indicates that the polarity of the voltage source will be opposing the direction of the main current. So this is the significance of negative sign coming into the expression. Now we do some problems. So state and proof we have finished. So now come to the there is a circuit. In this circuit R is changed 4 to 2 ohm. So this impedance is changed from 4 to 2 ohm. Verify the compensation theorem. So what we are going to do, I am going to find the I4 of this circuit, then I will draw the modified circuit, then we will find the current through this branch, then take the difference. Okay. Now the third step, I will draw the circuit for the compensation theorem. There will be the impedances and one injecting one EMF that will be injected in the modified branch, that is in the 2 ohm, and we find the change in current. If both the changes are same, then the theorem verified. These are the simple procedures. So come to here. So I4. So I4 I have just I can explain here how I have calculated. This 4 and 8. This 4 and 8 ohm resistor, they are in parallel. So 8 into 4, 32 by 12. And equivalent is in series with 1 ohm. So it is. So this is the equivalent impedance of this network. Okay, if you are looking from the source side. So and 1 volt. So I4, the current through this, that this is the total current. This is the total current. And I have applied the current division. If you want to find the current through this 4 ohm resistor, so using the current division, I have taken the 8 impedance of this branch divided by total impedance. So 8 divided by 12. If you want to find the I8, so here it will be 4 by 12. So this is the simple current division you have studied in your BTech first year course. So this is the I4. This is the original current I4, 2 by 11 ampere. Now I have drawn the modified circuit where the changes have taken place. So this 4 to 2 ohm. So I have taken here the 2 ohm. Then find the new value of I4 dash. So simple, this 4 and 8 they are in parallel, so 16 by 10, 8 into 2 16 divided by 2 plus 8, they are in series with 1 ohm. So this is the total impedance, equivalent impedance as seen from the source side, divided we divide in the voltage, we get this the total current, and then apply the current division here. So 8 by 10, simple. So this is 4 by 13. So this is the change in current. This is the I4 dash, this is the new current. Now consider change in current. So I4 dash minus I4, so it is coming 18 by 14 ampere. This is the delta I. Now we have to verify. So for the verification, what we will do, we draw a circuit equivalent to the compensation theorem. There what will be, we have inject a EMF in the modified branch. So in this branch we have the VCC. VCC will nothing but that will be the I4 into delta Z, and we will replace this independent ideal impedance source by its internal impedance. So internal impedance of this ideal source is 0, so it will be replaced by the 0 resistance wire. So look at, this is the circuit, or we can say the circuit to verify the compensation theorem. So I have injected this much voltage in modified branch while replacing the other energy sources, independent energy sources, by their internal impedances. So I have replaced. Now look at here. Now you have to find the delta I from this circuit. Okay. So delta I here, here, here. So first we have find the delta I, and then we have apply the. So VC is minus I4. This is the original current I4. This is the change in impedance. So this is 4 by 11 ampere. So delta I is equal to VC upon total impedance. So this 8 and this 1, they are in parallel. So 8 into 1 divided by 8 plus 1. So it will be 8 by 9. They are in series with this impedance. So it will be, this is the impedance of the network, VC upon this. So this is. So this delta I is from the circuit of the compensation theorem. And we have seen that delta I both are equal. So hence the theorem verified. So for the verification there are 3 steps. First, find the original current of the original network, then draw the modified circuit and find the new current, take the difference of these currents, that is step 1, we can say. The second step is draw the equivalent circuit of the compensation theorem, that will have only injected voltage, and that voltage will be in the modified branch. Replace the energy sources and find the change in current. If both are equal, then we can say that the theorem is verified. Now come to the another one. 5 ohm resistor is changed to 8 ohm. So this is 5 ohm resistor. The impedance of this resistor is going to change from 5 to 8. Determine the resulting change in current through. So what will be the change in current through this impedance? Okay. Using the compensation theorem. So using the compensation theorem, it means you have to draw a circuit having the compensating voltage in the modified branch, replacing all the energy sources by the internal impedances, and try to find the change in current. This is way. So look at here. So what we do? First we will find the value of the I. Once we get the value of I, then we will multiply with the delta Z. That will be the VC. that VC will be injected in this branch. We will replace this 10 volt voltage source by its internal impedance, and then we can find the change in current through the J4M. So look at here. So this is the value of I. We can see that this and they are in parallel with series with this. So this is the equivalent impedance of the network as seen from the source terminal. So this is the I. So the value of I will be this ampere. Then we will calculate the VC minus I into delta Z. So I is this and delta Z is 3. So 5 ohm resistor to 8 ohm. So delta Z is 3 ohm resistor. So multiplied with this 3 we get this VC. Now we will draw a circuit here. This is the VC, this is the injected voltage in the modified branch. So changes taking place in this branch. So I have injected this VC in this. I have taken the 8 ohm resistor, Z plus delta Z, then J5 and now find the value of delta I and then apply the current division at this node. We can get the value of this del I. So look at here. So delta I is equal to VC upon this and they are in parallel. So this is the equivalent and then they are in series with this. So this is the equivalent impedance as seen from the source terminal. So delta I is VC upon this. So this is the delta I. This is the delta I. Okay. Now apply the current division here. So if you want to find the current through this, so this delta I is equal to total current J5. This is the total change in current delta I and this is the impedance. So if I am going to find the current through this, so this impedance J5 divided by total impedance 3 plus J5 plus J4, so J9 into delta I. So we can find this. So this is the change in current in using the compensation theorem. So there are three types of questions may be asked. If it is purely theoretical, then they may ask state and explain and prove compensation theorem. The second question will be the circuit is given and you are required to verify the theorem. And the third one is using this type of questions may be asked. So for the verification we have discussed earlier, there are 3 steps. Step 1, original current, then draw the modified circuit, find the new current, take the difference. And the third step, draw the compensation theorem equivalent circuit, basically this circuit, and try to find the change in current. If both the changes in current are same, then the theorem verified, otherwise not verified. Okay. R1 is changed to 10 ohm to 12 ohm. Find the change in current through the 5 ohm. Simple. So procedure is same as we discussed earlier. So IR1 we can find out R1. So the impedance changes in here. So this is 1 ampere. Then VC IR1 into 2 minus 2 volt. Then draw the circuit required for the compensation theorem. So only this is the injected voltage. We inject this voltage in the modified branch where the changes have taken place, and then we try to find the change in current. So delta IR1. So delta IR1 is basically VC. These are in parallel. So 5 in 10 into 5 divided by 10 plus 5. So this we get 15 by, and they are in series with 12 ohms. So this is the delta VC upon this R1. through R1 and 5 ohm resistor. So I have now come to the 5 current, change in current through the 5 ohm resistor. So simple current division. This is the current division. Total current, this current is coming here, and then take the division here. This delta is coming here. Here now current in division, current through the this 5 ohm resistor will be 10, this impedance 10 divided by 10 plus 5, 15. So this here change in current. So change in current through R1 and 5 ohm resistor. Simple, find the compensating voltage to find the Vc and then change in the current. Use the compensation theorem. Simple, sir. Simple circuits. Only we have to take care of where we have to inject the voltage and how we have to calculate the Vc. That is the more important thing, or nothing else. Simple. They are in parallel. This and this are in parallel, so parallel, and they are in series with this. So this current. Then find the value of Vc, that is I minus I into delta Z. Draw the new circuit. This is the circuit required for the compensation theorem. We have injected this much voltage in the modified branch and take the delta I. So Vc upon they are in parallel with series 5 ohm resistor. So this is the equivalent as seen from the source terminal. So this is the delta I. So this way we can calculate the change in current in any other branch of the network using the compensation theorem. Now, what are the applications and limitations? To find the tolerance limit of the elements of the network due to change in impedances. Okay, so we have seen that whenever there is change takes place in one branch, the currents of other branches changes. So we know that if the network is resistive, then there will be I square R losses. So a lot of heat will be developed. So temperature of the circuit will go rise. So how much change we can tolerate? Okay, how much temperature a particular network or circuit can tolerate? So that can be checked. So if there is this much variation is taken place, so how much variations in current in other branches of, because in the network we have some sensitive elements there, so you have to take the care of those sensitive elements. Not applicable to network containing dependent sources. We know that if the circuit is containing only the dependent sources, it means there is nobody is to supply, because these dependent sources are depending on the independent sources. If there are no independent sources in the network, so who will provide the necessary energy to these sources? So we cannot apply this compensation theorem if the network is containing the only the dependent sources. Not applicable to nonlinear circuits. So what is linear circuit and what is nonlinear circuits? We have studied. A circuit is said to be linear if it obeys the principle of superposition. So what is principle of superposition? If it holds additive property and homogeneity property true, then it holds the principle of superposition, and then if the circuit satisfies the principle of superposition, then circuit is said to be linear, otherwise circuit is nonlinear. So look at the summary. What we have discussed what is compensation theorem, statement of the compensation theorem. Then we also proved it with the help of taking the equivalent Thevenin equivalent of the circuit. Then we discuss what are the steps required to verify a compensation theorem. So, there are 3 steps. Step 1, we first find the original value of current. Value of current. Say this is I. Then original value of the current in the given network. Okay, it must be written here, given network. First step. Second step is draw the modified circuit. Draw the modified circuit. And find the new value of current in the modified branch. Then take the delta I. Say this is I dash. So I dash minus I. Then third step is draw the circuit. We can say the compensation theorem circuit containing your compensatory voltage Vc is equal to minus I into delta Z, and replace all independent energy sources by their internal impedances. Okay. Then find the value of delta I. If this di, this and this, if they are equal, say this is delta I, and if they are equal, then the theorem verified. So, there are 3 steps. Then we also discussed applications and limitations. Applications, we cannot apply the network containing only the dependent sources, and if the circuit is nonlinear. An application just to check the tolerance limit of the network, because network contains the sensitive elements. If the temperature goes beyond a certain limit, so it will burn the circuit elements. So, these are some applications and limitations of compensation theorem. I hope you understand all the things. If you have any query, you can write mail to me. I will sort out your problems. So, I stop here. Thank you very much. Jai Hind.